12,000 able-bodied male undergraduates at the University of Illinois participated in required physical training. Each student ran a timed mile. Their times followed the normal distribution with mean 7.11 minutes and a standard deviation of 0.74 minutes. An SRS of 100 of these students has a mean time x, which is equal, mean time, it should say, mean time 7.15 minutes. A second SRS of size 100 has a mean of 6.97 minutes. After many SRSs, the values of the sample mean x follow the normal distribution with mean 7.11 minutes and standard deviation 0.074 minutes. What is the population? Diana?
All able-bodied male undergraduates.
Yeah. So the 12,000 able-bodied male undergraduates, I like how they call them able-bodied. At the University of Illinois. What was the mean of the population? .11, right? It tells us they each ran a timed mile and their times followed a normal distribution with mean 7.11 minutes. It's the population, so we use mu. Standard deviation 0.74. What is the mean and standard deviation of the sampling distribution? Now there's a lot of numbers thrown around after those first two, but if you actually read it, it says the values of the sample mean follow a normal distribution with a mean of 7.11 minutes and a standard deviation of 0.074 minutes. So the mean for our sampling distribution, we use x bar. It's still 7.11 minutes. So the statistic was a really good estimator of the parameter. It was unbiased. It didn't overestimate or underestimate. And the standard deviation is 0.074. So that's the only thing that is different, is the standard deviation of the sampling distribution is lower than the standard deviation of the population by 10 or 100. My brain's not working. So, like I said, I'm going to go quick today because I have to leave.
Speed run. I can take over.
All right. I forgot my Reese's Pieces. I'm sorry. So we're going to pretend I have my Reese's Pieces here. We're going to say a large bag has 1,000 pieces. By the way, what colors are Reese's Pieces?
Orange. And yellow.
Okay. I heard orange and brown a lot, and then Nate told me yellow. There's 3 colors. There's orange, brown, and yellow.
Yes. Whoa. Dude, what?
Exactly 40% of the candies are orange. We're going to take a sample of 50 pieces. So we're going to define X to be the number of orange candies in the sample. So what are all the possible values of X? We take a sample of 50 candies. What are all the possible values?
20.
That'd be 40%, yes. Am I gonna have exactly 20 out of 50 be orange?
No.
Could I have less than 20?
Yeah.
Could I have more than 20?
Yes.
Could I have no orange
Yeah.
at all? Could I have all orange?
Yeah.
Yeah, they're very unlikely that I have no orange or all orange, but it's possible. So all the possible values for x go all the way from 0 to 50. No, I'm not going to write them all out. I'm going to use my favorite punctuation, which is the ellipse. It's not the shape in math. It's an ellipses, right?
Yeah.
Okay. But you could tell, though, I'm a math person. I'm like, it's an ellipse. No, it's not. All right, so what type of distribution does x have? Normal. We've learned about normal distributions, binomial distributions, and geometric distributions. So is it normal, binomial, or geometric?
Geometric.
Why do you say geometric?
Because there's no. It's like
You're wrong.
That was harsh. Why do you say he's wrong, Noah?
I get to
All right. Hannah?
stuttering too much.
It's binomial because there's a set number.
Oh.
That's our n in bins. We have to check the other 3 as well. So we have B, which is binary, success and failure. So what's a success? Getting an orange candy, and a failure? Not orange. Now the I is, boys, thank you. The I is the difficult one. It's independent. It's the one that is my least favorite. It doesn't say independence, but if I don't have independence, my whole lesson kind of falls apart. So we're going to assume there's independence, okay?
Yeah.
Hannah reminded us of the N part, says set number of trials. We're looking at 50 candies. And then S, the probability of success, 0.4. Now I'm really going to ask you to reach back in your brains. How do we find the mean and standard deviation of binomial distributions? Cheyenne? The mean is n times p.
Wait, what's n again?
Number of trials. So our mean would be 50 times 0.4, or 20. Anybody remember the standard deviation? Nate?
It is square root of np parentheses 1 minus p.
Thank you, sir.
That's what I was gonna say.
I'm sure it was what you were going to say. So square root of n times p times 1 minus p, which would be 50 times 0.4 times 0.6. And then square root of 12, 3.464. Sorry, my 4 looked not so pretty. So, can I move it up slightly? can we sketch an approximate probability distribution for X? Do you remember how? You're like, of course we can. You put it there and you left a big space. So yeah, we can. Anybody remember how? What did you do, Maddie? Maddie made a normal curve. Can we use a normal curve?
Yeah.
Why?
Yes.
Because. Facts.
We can use a normal curve.
We have the standard deviation.
We
That's what I'm saying.
we have two conditions we have to check to be able to say we can use a normal curve. What were those two conditions? Say it louder. I'm
Gotta
deaf.
be bigger than 10.
What's got to be bigger than 10?
Yeah,
The mean n times p has to be greater than or equal to 10, so the mean has to be greater than 10, which it is. The other one is the number of failures, right? N times 1 minus p. This is the number of trials times probability of success. So really that's the number of orange candies we expect, the number of successes we expect. So this is the number of failures we would expect. And if out of 50 candies we expect 20 to be orange, how many would we expect not to be orange? 30.
Yes, we can use it on most.
So yeah, we can, because the number of orange candies and not orange candies, success and failures are both greater than 10.
Yes.
Did you have a question? I felt like I saw a hand over here, sorry. So we can use our normal curve. I had you find the mean and the standard deviation above. So our mean is 20, standard deviation of 3.464. And then, of course, we would label it 20. This would be 23.464. I'm not going to actually label them all because I'm crunched for time. I'll do the first two. Now, so far we've focused on counts. So the count of the number of candies, the number of cherry starbursts. We've focused on counts. We're going to get away from that and we're going to focus on proportions. And if you read my sentence, I say in this section, and this is kind of how the rest of your textbook is broken up. When we start a chapter, we're going to focus on proportions for the first few days, and then we'll use the same idea but with means. So when I say in this section, right now we're at section 7.2 in the textbook, we're going to focus on proportions. When we move to section 7.3, we'll switch to means. Use the same idea but with means. And it'll be that way for pretty much the next 8, 9, 10, 3 chapters. We focus on proportions, then we switch to means. So how do we turn all of the values for x into proportions? So here's all the values for x, right? 0 through 50. How do we turn it into a proportion? Let's say I had my sample of 50 candies and 17 of them were orange. How would I find the proportion?
Divide
By
50.
50. And why did you say 50, Sam?
That's the total amount.
So if I had brought our candies, we would divide by 50. But if we're just looking at any sample in general, we divide by whatever our sample size is. So if we were to take a sample of 50 candies and record the proportion of orange candies, what would we expect to get? Say that louder.
50 divided by 20.
Other way.
20 divided by 50.
We expect to get 20 orange candies, and when we divide by 50, we would get 0.4 back, our probability of getting an orange candy. And just like we talked about when we were coming up with the list of possible x values, are we always going to get 0.4 for our proportion of orange candies? Yeah. And the reason why is because every time you take a sample, there's some variation known as sampling variation. Every sample is different. So see, this is where I was going to give you guys candies. Have you count the number of oranges. So since I don't have the candies, here's what we're going to do so that it's random. I want you to get out your calculators. I'm going to have you pick a random number between 1 and 50 to get, I should say 0 and 50, to get your number of orange candies, because I suck and forgot the candies. All right. Okay. Quiet down really quick. So, I apologize. I will bring you the candies a different day. So that you're getting a random number. We have the list of all possible orange candies. It goes from 0 to 50. So don't start at 1. Go to 0 for your low number. 50 is the highest, and you just want one number. So those of you that it prompts you, 0, 50, 1. Those of you that are using an older calculator like me, we're going to do 0, 50, 1. So in my sample of Reese's Pieces, I only got 7.
I got 35.
You got 35?
Yeah.
Okay. So I got a p hat of 7 out of 50, which is 0.14. Oh, sorry, thank you. Zach said he got 35. So 35 out of 50 would be 0.7, right?
Yeah.
Maddie was really excited, so I'll ask for hers. You got 14 out of 50. Why were you so excited then? Okay, what's your proportion though?
14 out of 50 equals 0.28.
0.28. Who else wants to volunteer? Molly? You got what? 0.2 or 20 out of 50? So 0.4. Cheyenne?
0.54.
Nate? You raised your hand too.
0.16.
0.16. Jillian?
0.74.
That's a great.
Calvin, what was yours? Eric?
0.5.
You got
Yep.
I didn't even get to say exactly 25, and you said yep. Michelle?
What do you get? 0.7.
I know.
It's 1, 2, 3, 4. I need one more. Hayden! What'd you get?
Extrapolation.
All right. Now, we're going to make 2 sketches down below. So I suggest putting a dashed line in between.
What's this job like?
Well, it's a software program that I was going to show you, but as my life goes, this is what the Java applet is doing at the moment, not loading. It's just my life this week. Nothing is working the way it's supposed to. I just, February is 2 days in, and I'm ready for February to be done.
January.
He hates Valentine's Day.
Oh, I got my There's one.
All right, so I have from 0 to 0.8 by 0.1 for my number line, because we're going to graph our samples that we took. We do, we're either going to have 2, 4, 6, 8, or 0 is the last decimal. So if you want to, you can put the 4 little dashes in between each of these. It's not that bad. I mean, mine aren't like perfectly spaced. My number line has a hill in it, so.
Yeah, you think yours is bad? Think about us who like haven't been doing it that long.
Facts.
All right. So, we're gonna plot these ones. So I had 0.14, which is right here. Then we had 0.7, 0.28, 0.4, 0.54, 0.16, 0.74, 0.5, 0.7, and then Hayden's fib of 0.54.
Okay, wait, that is
I got that one.
Really? How'd you get it? How many orange candies does that mean you had?
27.
If only he wasn't so good at quick math. All right. So, this is, I know it's not the whole class, but like I said, I am strapped for time. So we're going to say this is our class sampling distribution of p hat. Now, I told you at the beginning that the proportion of orange candies is 0.4. So we're going to find the center. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots. So the center is the 5th and the 6th dot. So we have 1, 2, 3, 4, 5, 6. So it's these two, 0.5 and 0.54. So our center is at 0.52. So do I have bias present?
Yes.
Did we overestimate or underestimate? We overestimated. What about our variability? We have quite a bit of variability. The highest is 0.74, the lowest is 0.14. So we have bias and we have high variability. What the Java applet was supposed to show you, first of all, we're going to increase our sample size to 50. No, excuse me, we were going to take 500 samples, 50. We took size 50 samples. We were just going to look at a bunch more, but my life sucks right now, and it didn't want to work. So what I was gonna show you is that as we took more and more samples, same size, and I'm just gonna use an old sketch from a previous year. I know I'm cheating, sorry. It went from 0.2 to 0.6. And there were 500 samples. I'm not going to put 500 dots. I'm just going to make the basic shape for you guys. It becomes to look pretty normal. And the year, that's what I did, just dot, dot, dot. I just was more quiet about it. And the Java applet would have told us the center of our distribution, which it wasn't 0.4. It was 0.402. So just a tiny amount. Boys, thank you. Just a tiny amount of bias. Variability went down. We went from 0.6 for our range to 0.4. What could we do to make the variability even lower? Not add more samples, take bigger samples. Okay? So if we increase the sample size bigger than 50, it's going to help lower it. So this was supposed to be, we'll say, the Java sampling distribution, because my Java applet didn't work. I'm very mad about that. Over here, we had a high amount of bias and high variability. Variability. Struggle with that word. Here we had low bias, and I would say moderate variability. It's still pretty spread out, but not as much as our class sampling distribution. Can I move it up? All right. So we already kind of talked about this, but I didn't specifically write it out. So we're going to talk about the mean and standard deviation of the sampling distribution of p hat. So we're going to start with the mean and standard deviations for a binomial variable. Thank you, ma'am. Which Cheyenne reminded us of the mean, and Nate told us our standard deviation formula. And then we talked about how to change the count of candies into proportions, and Sam told us to divide by the sample size. So if a binomial measures the number of successes out of n trials, how do we change them into proportions? We divide by n, because that's our sample size. That's a really bad arrow, sorry. So if we want to find the mean of p hat, we're going to take n times p, and we're going to divide by n, which then the n's cancel out. So the mean of p hat is just p, the given parameter. Which, when we did that with the orange candies, I'm going to flip back really quick. I told you that 40% of the candies were orange, so we knew the probability of success was 0.4. And then Sam reminded us that if we wanted to take our expected value of orange candies and turn it into a proportion, we'd divide by the sample size. And hey, look, we got 0.4 back. So it makes a whole lot of sense that the mean of p hat is just p, your probability of success. The standard deviation, slightly a little more complicated. So we have n times p times 1 minus p, and we're going to divide that whole thing by n. They simplify it by squaring the bottom so that we can put it all under a square root, and then you have n over n squared, so the n on top cancels 1 on the bottom. It's algebra. I can show it to you if you want me to, but it simplifies down to the square root of p times 1 minus p all over n. You can either, if you want me to show you, I can, not today, or you can just trust me, I'm not lying. It does simplify to that. So the mean of the sampling distribution of p hat is equal to p. Put another way, that means p hat is an unbiased estimator of p. Because our statistic, p hat, should be centered right at p, our parameter. The standard deviation of the sampling distribution of p hat is equal to the square root of p times 1 minus p divided by n, all of it under the square root. That is true only as long as the 10% condition is satisfied. So I can't remember who asked me the other day about sample sizes and when a sample size was large enough. And I said you can't take more than 10% of your population. That's this 10% condition. So our sample size, little n, has to be less than or equal to 1/10 of the population. The minute we go over 10% of the population for our sample size, this formula can't be used anymore. And hopefully the sub shows up soon. I have one more though. So we know that a bag of Reese's Pieces contains exactly 40% candies that are orange. If we select a random sample of 50 candies, what is the probability that the sample will give a result within 2 percentage points of the true value? So first of all, a result within 2 percentage points of the true value. So we know that p is 0.4. So when I say within 2 percentage points of 0.4, what's the range we're looking at? 38 to 42. But we're going to use decimals. So this tells us we're looking at 0.38 to 0.42. We already checked the conditions for normal, but just to remind you, to use a normal curve, you have to check that n times p is greater than or equal to 10, which it was 20. N times 1 minus p is greater than or equal to 10, which we did on the other page, and it was 30. So we can use our normal curve. Now, we have new formulas when working with proportions. The mean of p hat is equal to p. So that one's not really a formula, it's just that our mean is going to be 0.4 like it was stated. The standard deviation of p hat comes from the square root of p times 1 minus p divided by n. And we can only use that if our sample size is less than 1/10 of the population. So we have to check that n is less than or equal to 1/10 of our population. So is 50 less than or equal to 1/10 of, and I should have put it back in here, but way back at the beginning, I told you a large bag has 1,000 pieces, so our population is 1,000. And 1/10 of 1,000 is 100. So that is, 100. That is met. So we can use that formula. So p is 0.4, which means 1 minus p is 0.6. And then we're going to divide by 50 and then square root that. So our standard deviation is 0.069. So we have 0.4 at the middle. This would be 0.469. To save on time, I'm only going to go one above and below. So 0.4 minus 0.069, 0.331. Plus, we're looking at 0.38 to 0.42, which falls inside both of those. So we'll say 0.38 is about here-ish, and 0.42 we'll say is about there-ish. So that's 0.38, 0.42, and we're looking for the shaded area in between. It's a normal curve. We have our lower bound, our upper bound, our mean, and our standard deviation. So we just have to put it into the normal CDF function. Lower bound 0.38, upper bound 0.42, mean of 0.4, standard deviation of 0.069. Sorry, 0.069 got really small. Number 2, 0.38, 0.42, 0.4, 0.069. So we get 0.2281 when I round. So about 22.81% of the time we take a sample of size 50 that contained the true proportion that was within 2 percentage points of the true proportion. Any quick questions? Don't know why the sub's here.
Is it sub?
There's supposed to be a sub here.
Okay.
I'll be going this soon.